Hello, calculus fans! So we're going to start talking about differential equations and modeling real-world processes with differential equations. What we want to do is create a mathematical model for these real-world processes. We'll get our model from intuitive reasoning, or sometimes we'll use a physical law that we derive from experiments. The model is usually going to take the form of what we're going to call a differential equation. A differential equation is an equation that involves a function, an unknown function, and some of its derivatives. Usually an algebraic equation, the thing you're solving for is an unknown number. A differential equation, you have an unknown function. So we have models of population growth. So one model for the growth of a population is based on this assumption that the population will grow at a rate proportional to the size of the population. That's actually a pretty reasonable assumption when you have things like bacteria or animals, but you need to have ideal conditions. There needs to be an unlimited environment for the population to grow, plenty of food, no predators or diseases that will eliminate these creatures. All right, so let's identify and name some of the variables in our model. So t is time, that'll be our independent variable. And p is the size of the population. That's our dependent variable. Now our rate of growth is the derivative. Remember, the derivatives represent rates of change or rates of growth. So that's dp by dt. And then we made an assumption that our growth rate is proportional to the population size. So the way we'll write that is dp by dt is equal to k times p. K is a proportionality constant. We're saying that the population growth is proportional to the population size. Now this is a differential equation because the unknown quantity is a function. Remember, algebraic equations, unknown quantities are numbers. Here we have an unknown function. And then the equation has p and its derivative. Now we should see that as long as the population is positive, and that's all we really care about, we don't care about a situation where the population is 0, and it doesn't make sense to talk about negative population, then the derivative is itself positive. We're thinking of that proportionality constant here being positive. So the population is always increasing. And in fact, this shows that as the population increases, that the growth rate also increases as the population increases. Now what we really want is a solution to this differential equation. So the equation tells us that we want a function whose derivative is a constant multiple of itself. Now exponential functions have that property. When you differentiate an exponential function, you get the function itself. Or sometimes you get a constant multiple of that function if there's something on the inside. So here's a general form. If we have p of t is equal to c times e to the kt, then p prime of t is equal to c times k e to the kt. And if we pull that k out, then we can see that we just get k times the original function. That tells us that any function of the form c e to the kt is a solution of our differential equation. And then later on we'll actually see that there are no other solutions. The last thing to note is that when time is equal to 0, p of t is equal to c. So in fact c represents the initial population of whatever we're modeling. Keep in mind that we are solving this differential equation, or at least writing down a solution for this differential equation, under these assumptions that our model has, which is the unlimited environment, unlimited food, no predators, no diseases. So we'll see later on that we'll have, when we make more stringent assumptions, we'll have to have a more complicated model. Okay, that's all for now.